Hello, my name is Victoria Grimes, and this is my Lab 5, Analyzing the Motion of a Slinky. The purpose of Lab 5 was analyzing the motion of a falling slinky, where the system is the Earth and the slinky, observing the slinky falling with the tracker application, analyzing the motion and position of the bottom of the slinky relative to the top of the slinky, constructing computational models based on foundational principles of Newton's second law, and comparing the models with observations and drawing conclusions about the slinky's motion. Some of the fundamental principles and models in this lab were Newton's second law and drag. Newton's second law relates the net interaction between system and surroundings to changes in momentum or motion of the system. An object's change in momentum is dependent on the net external force, and drag is a force whose direction is always opposite to the direction of the object's motion and has a magnitude proportional to the square of the distance. Drag is happening because as the object falls, it is interacting with other particles, for instance air, who slow the object's motion down, and this will be working in the positive y direction for this slinky situation. Furthermore, we'll be using the velocity update formula and the position update formula for the code later on. The video on the left, as you can see, is a video of the man dropping a stretched slinky from rest. The video on the right is where I put the footage into Tracker to get the position and time information I later put into the computational models. As you can see, the bottom of the slinky stays fixed at the origin while the top moves down. This is the case up until second 5, where the bottom and top of the slinky meet. They then fall as one single mass. Shown here is the position versus time graph for the observed motion of the slinky. There is no displacement until around second 5, where the slinky begins to fall as one mass. I inserted this data into the computational model based on data I received from implementing the tracker application. So the start time was 0 seconds, the end time was 12.2 seconds total, our time step was 0.04 seconds, the initial velocity was 0 meters per second, the initial position was 0 meters, and our mass was 0.25 kilograms, and our proportionality constant, B equals 2.6, was found experimentally to also account for drag and slow motion in the video. For the code, I inputted the information from the previous slide into WebVPython to create this computational model. In the while loops, the position update and velocity update formulas were used. This time frame is for when the slinky is falling as a single mass. In this part of the code, this time frame in the calculation loop accounts for the entire time of the slinky's motion. Shown here is the position versus time graph for the computational model's motion of the slinky. There is no displacement until around second 5, where the slinky begins to fall as one mass. Here, the line is more stable and the decline is constant. Presented here are the observed data and computational model graphs. The pink line is the actual or observed data. The blue line is the computational data model. As we can see in the experimental data, the slinky did not fall as far as in the computational model. However, in both models, there is a displacement beginning around 5 seconds where the slinky begins to fall as one mass. Now we have reached a conclusion and discussion, and so we think, how do we describe the slinky's motion? Well, the bottom of the slinky stays at rest as the slinky was dropped from static equilibrium. The tension and gravitational forces cancel out initially up until we reach that 5-second point, and the slinky began to fall as one singular mass after the top met the bottom. We cannot do conclusion and discussion without first talking about errors. One possible thing is human error when dropping the slinky and recording the motion in Tracker. Another source of error is that the proportionality constant was found experimentally, so maybe it is not as accurate.